Water quality is a important issue for a variety of reasons. Um, here's a person from Cambodia who has consumed water with arsenic for a long period of time and has the effects of chronic arsenic poisoning. So obviously that's an important societal impact of poor water quality. And other issues related to water quality shown here. This is kind of a stark example of some chemical contaminants that could be introduced through poor waste handling practices and cause contamination of groundwater that can lead to a variety of problems. This is an illustration of some computer-generated depiction of a plume in the subsurface that's been identified through these wells. So I want to talk about water quality over the next few minutes and address the different compounds that can affect water quality, and then later on we'll talk about contaminant conceptual models and some of these other issues. So how do we tell when some water is contaminated? Well, in the U.S., the EPA has a list of contaminants with concentrations that it sets as the maximum contaminant level that's allowed in drinking water. And this is used as the standard for acceptable concentrations in this country. There are 6 different categories of compounds recognized by the EPA, and they're shown here. Microbes, inorganic compounds, organic compounds, and radionuclides. Those things occur naturally, and disinfectant byproducts, these are a result of the water treatment process. And all of them can form hazardous compounds that come under the jurisdiction of MCL. So you can find out more about this by going to the EPA site, and you can see here this is a list of contaminants, and here's the MCL, and this is quite a long list, and it's broken up into these different categories. So this defines whether the water is contaminated in a legal sense, or healthy, or it's okay, and basically, for many of these categories, some low level of concentration is acceptable in drinking water. You can see actually for this one, cryptosporidium, the MCL is 0, or this is, I guess, the MCLG. This is a case where you really don't want to have any of these kinds of bacteria in the water. But for organic and inorganic compounds, there's a concentration threshold that's defined by the MCL. So if we look in general at the compounds that affect water quality, there are 2 big types of categories. One is dissolved, and the other is where the water and the compound exist as separate phases. So if a compound is dissolved in water, then you only have the water itself as a separate entity. The compound that you're interested in is dispersed amongst the water molecules at the molecular level. Many compounds do that, but some compounds won't. They all exist as a separate phase. And so there are distinct regions of water and distinct regions of something else at scales somewhat greater than the molecular scales. And the something else could be a solid or a liquid. So dissolved compounds come in a variety of different flavors. You can have gases as a dissolved compounds, or ions, inorganic compounds, or organic compounds that are dissolved at the molecular level. The gases here that are fairly common, nitrogen and oxygen, these are just from the atmosphere. CO2 also from the atmosphere is dissolved in water. quite commonly. These other compounds are less common, but they can be more hazardous. Hydrogen sulfide is a very toxic compound. This is the stuff that smells like rotten eggs. It's quite toxic, and so that's something to be concerned about if you smell that rotten egg smell. This is radon, also potentially quite hazardous compound, and methane. Methane will dissolve in water, and you guys have probably all seen the picture of the flaming faucet associated with fracking. It was in some popular movies, and this generally is methane that has dissolved in groundwater, been pumped up, and the pressure drops as it gets pumped up, and that causes the methane to come out of solution. Just like if you were to open a bottle of beer, the CO2 comes out of solution, the methane comes out of solution, and then ends up in the atmosphere outside of the faucet and can then burn. Major ions, these are important. These occur at least to some extent, in all water, in various proportions. Calcium and magnesium, potassium and sodium are the main cations that you find. Sulfate, bicarbonate, in some cases carbonate, chloride are the main anions, and nitrate is also an important anion in some cases. And then there are also trace ions that are important. These are many of these here are metals that can be quite hazardous, so they're important as potential contaminants. Inorganic, non-ionic compounds. These are all inorganic but ions. But the main example of an inorganic compound that's not an ion is silica. And silica occurs in water at fairly low concentrations, but concentrations that can be important. And then there are naturally occurring dissolved compounds that are organic. These are fulvic and humic acids, and you may have seen these in some streams in South Carolina. The streams that are in the coastal plain, in the lowlands, have a dark brownish kind of tea color. This is an example. I must say it's not very appetizing. It causes the water to be quite a various colors of brown, various shades, and they're naturally occurring, and generally they're not harmful, but they give the water kind of an unappetizing color to it. And then there are man-made organic compounds that are dissolved in water, and the fuel and solvents are the two main ones. There are also pesticides and herbicides that are dissolved in water, and these are, of course, hazardous compounds that form environmental problems. Okay. So those are dissolved compounds. Then we can also have compounds in water that exist as a non-aqueous phase liquid. And you see this acronym around a lot, NAPL. And NAPL is a liquid that occurs as a separate phase. And we distinguish two different types of NAPLs based on their density. If the density is greater than water, then we call that a DNAPL for a dense non-aqueous phase liquid. And of course then the density is less than water, that would be a light NAPL. Dense NAPL, those things will sink. So when they reach the water table, they'll sink down through the water table and go down to depth. That can be a problem because that material then can be spread out over a wide range of depths and difficult to find. Chlorinated solvents, these are the main DNAPLs, but Dry cleaning dry cleaning fluid is a type of chlorinated solvent. Wood preservative, the compounds that they put in transformers, all these are organic liquids that are denser than water and sink. So here's some acronyms: TCE, PCE. The C stands for chloro in all of these cases, and the chlorine, gives it the higher density. So these guys are all chlorinated solvents. This thing here, and they're used for degreasing various industrial processes. And as it turns out, they work great. They're fantastic degreasers and work very well, and so they were quite popular. But the problem is that they're also carcinogenic, and they were used a lot, and they also then got away from people who were handling them. They leaked, or they were in tanks that leaked, or they were spilled, and they formed contamination. The elm apples, they float on the water table just like this oil is floating on the water. And by and large, these are fuels like gasoline or cutting oil or oil for your car's engine. And in general, they're hydrocarbons. So fuels and oils are hydrocarbons. Natural crude oil is also a hydrocarbon. So all of these compounds are lighter than water, and they float when they're on the water. Now, the big problem here if you look at fuel, gasoline consists of many different compounds. It's like this big stew of different organic molecules, over 200 compounds. Of that, there are many compounds that probably are not hazardous to you, but there are some that are, and the ones that exist in highest concentration that are the most hazardous are these guys: benzene, toluene, ethylbenzene, and xylene, and they go by this acronym BTEX. So the BTEX ingredients in gasoline are the ones that are the most hazardous, and they're the ones that drive the risk at these kind of sites. So I guess I should say too that all these compounds exist as separate phases. So if you mix them together with water, you can see some phase that's the non-aqueous phase liquid, and that's pretty clear cut. But what you can't see is that some of the molecules that occur in this non-aqueous phase liquid also will dissolve into the water itself. So if this is some gasoline, the gasoline exists as a non-aqueous phase liquid, but the components of the gasoline will also dissolve into the water. Okay, so the previous slide that showed dissolved compounds, they can be coming from these non-aqueous phase liquids. So there are a variety of solids that can cause problems, and at the top of the list here are these microorganisms, and in particular, the particularly bad actors tend to be microorganisms from fecal sources, either animal waste or human waste, and the reason is that these organisms have been associated with mammals, and so they interact with mammals, and some of them then can have very bad reactions and can be pathogenic. And so in that case, these microorganisms are very hazardous in low concentrations. A good example of this is cholera. Cholera is transmitted in drinking water, and it is a very hazardous compound. A very hazardous bacteria, causes very serious illness. Now, there are also inorganic compounds that are solids that occur in water, and these are small compounds on the micron, or small particles at the micron or submicron size level, and particles at this size can be suspended in water just because of Brownian motion. The jostling around of the molecules in water will keep these small particles in suspension. Clay minerals are an important kind of colloid. They're in this size range, but also small mineral precipitates. And here are some examples of different concentrations of colloids in water. When you analyze for the colloids, you use a measurement called the turbidity, and turbidity is measured as basically the ability of the water to block light that's transmitted through it. So a turbidity meter has a light source and a photodetector, and it measures how much light is able to get through the water. So you can see, I think, from these different samples that different magnitudes or different amounts of light would be able to get through these samples, resulting in different turbidities. A simple way, so this is an instrument that has a light source and a photodetector. A simple way of measuring this is to use this thing. This is called a Secchi disc. And Secchi discs are available in a couple of configurations. One way, and the way that this one is used, is to lower it down, usually off a boat, into surface water. And you look down and you determine how deep you can lower this thing and still see it. And eventually it goes deep enough so that you can't see it, and the turbidity of the water will affect how deep it can go. So they've calibrated the depth that you can see a Secchi disc with the turbidity, and so this gives you a way of estimating the average turbidity in the upper part of surface water without having to have a device where you take the sample out and measure it. And it's nice too because it gives you kind of an average over a few feet of thickness. There's also instruments where you have a little pattern like this, a little Secchi disc pattern at the bottom of a tube, and you fill the tube with water, and then just look down at it and see how much water you can have in the tube before you can see that this pattern on the Secchi disc. Okay, so the reason that solids are important as a contaminant is that the solids themselves may be problematic in the case of pathogenic bacteria or other coliform bacteria, but also the mineral colloids that we just saw on the previous page, the small clay particles or other precipitates, those things they may be harmless unto themselves, but they're fairly reactive surfaces and they tend to get things sorbed to them. So other contaminants can sorb to the colloids, and also microorganisms. Microorganisms will tend to stick to these solid colloids. So you can have a process called colloid facilitated transport, where compounds like metals or radionuclides or even bacteria that might not otherwise be mobile in water can move around quite readily if they storb onto these colloids. So that ends up being quite a significant issue because basically it can take a compound that you might think is immobile because it would stick to solids, but if it's sticking to a solid that's small enough to be mobile, then you can have a problem. All right, so I went through and made some unofficial statistics about contaminants, and these are based just really on my experience. I didn't bother to look these all up, so maybe I'm off a little bit, but I think these will be generally okay. So let's go through these, and you guys should just write down what you think the answer is. So the most common contaminant in general. So write down what you think the most common contaminant is. Okay, so let's see. What I said was sodium and chloride from seawater. So the most common contaminant based on like per volume occurrence. There's lots of sodium and chloride in seawater that's contaminating, or basically that's rendering water unusable by man. That by volume, that's by far the biggest. So what about the most common man-made contaminant? So write down what you think the most common man-made contaminant is. So there are a variety of man-made contaminants, but what I put here was that nitrate is the most common one. And the reason is because it occurs as a result of agricultural practices. You can have it formed as it's a fertilizer. Also, animals will produce it. So if you're raising animals, if you have it concentrated in a feedlot, for example, that can be a source of high nitrate. Even if you're not raising them in very high concentrations like a feedlot, if you have cattle that you're raising, those cattle tend to like to hang out together, and they have what's called cattle loafing areas. So the cattle like to hang out and loaf, and so they're hanging around in the same place, and they create a lot of manure in that area. And so there was a guy at Clemson actually that studied this and found that these areas that were cattle loafing areas were sources of nitrate contamination because of high density of manure there. So, the most hazardous on a per concentration basis, I gave that one away. What I think is probably the most hazardous contaminant on a per concentration basis is pathogenic microorganism, because it may take only one microorganism to affect you. Now, this is probably not actually possible. You probably have to have more than one microorganism. But I think the point here is that pathogenic microorganisms at very low concentrations, because they have the ability to multiply, just very low concentrations can be very hazardous, have a very bad outcome. So what about the most hazardous non-microbial concentration or contaminant? What do you think that would be? Most hazardous compound that is not a microbe. So what I said was that it was radionuclides. And the reason for this is that if you look at the MCLs for different compounds, radionuclides have very, very low MCLs. All right, so let's turn our attention to organic contaminants. These are going to be probably the main thing that environmental hydrogeology consultants are dealing with. So the most common organic contaminant is fill in the blank. So in order for it to be a common contaminant, it has to be used pretty commonly. And I think the most common organic compound to be used out there in the real world is gasoline. Gasoline is they have the gasoline stations, close to almost everywhere. And so the bad actors in gasoline are BTECs. And if you look out at older gas stations, the ones that are probably several decades old or older, virtually all of the gas stations that were built before the 60s, say, or even before the 70s, they used metal tanks, and those tanks would rust and leak. So BTEX is quite common. And so what about the compound that is the most problematic in the U.S., the groundwater contaminant that causes the most difficult problems in the U.S.? As it turns out, BTEX is the most common, probably the most common groundwater contaminant, but there are techniques for dealing with BTEX that are fairly straightforward. But the one that's the most problematic is not an LMAPL. It doesn't float like BTEX compounds do, but it sinks. So the most problematic compound in the U.S. would be, go ahead and write down your answer. So what I said for this one is that it would be TCE. This stands for trichloroethylene. This is a common industrial solvent. It has been widely used in the past, and it's very difficult to remediate. Okay, and finally, what compound causes the most health problems worldwide? And it's not TCE or BTEX or radionuclides. It's really none of the above. So even though maybe it's not the most common or most problematic, it does cause the most health problems worldwide, at least on a number of people who are affected. So write down your answer on this one. So I haven't really seen statistics on this, but the number of people that are affected by arsenic poisoning, like the guy that I showed you on that first slide, is in the statistics for arsenic poisoning in Southeast Asia are something like 10 million people. And it's been called the biggest mass poisoning in history. So I had to go with arsenic as the thing that causes the contaminant that causes the most health problems worldwide.